Yeah, okay. So what I'm going to talk to you all about is a package I've been developing called Halotools. I've released 0.1 last week. So Halotools gives a platform for building and testing models of galaxy evolution. In particular, Halotools gives a framework for starting from a model for how galaxies are connected to their underlying dark matter halos and generating Monte Carlo realizations of a galaxy population that can be directly compared to galaxy survey data. So if you're familiar with Boltzmann solver codes like CAM and CLASS and CMB-FAST, you can think of Halotools as being analogous to those, except whereas CAM generates CMB predictions, Halotools generates predictions for large-scale structure observables like galaxy clustering, galaxy-galaxy lensing, redshift space distortions. So when you couple Halotools together with a cosmological simulation, what you get then is essentially a prediction engine that you can compare to galaxy survey data. So before I talk about the package, I should say that Halotools has been, it's a collaborative effort. So Duncan Campbell is a graduate student at Yale who's done a lot of work on Halotools. Eric Tallerud has had major contributions to the package. And at least a dozen scientists have contributed anywhere between code fragments to direct pull requests to the code. And when I started off developing this package about a year and a half ago, I knew essentially no Python at all. I was a straight IDL programmer. And it was enormously helpful to have the AstroPy package template to work from because it basically freed me to learn how to write good Python code without having to, in addition, have this big overhead of also learning about package structure and how to develop test runners that were robust. And there's a huge amount of extreme conveniences that using the package template basically made this possible in a reasonable time scale. So a lot of people in this room have also contributed this, to this package just by virtue of making the package template so useful. So okay, a quick background on the science that Halotools is built upon. So the idea is to take a cosmological simulation, say an n-body simulation of the distribution and evolution of dark matter halos, and to create a galaxy distribution, which represents a model coupled with this simulation. So you need three basic ingredients to go from a simulation of cosmological structure to an actual set of observational predictions. So you need the simulation. In particular, you need a catalog of dark matter halos identified in the simulation. You need some model which connects galaxies and their properties to the underlying dark matter halos. And then you also, you see, you don't actually compare when you have a mock universe. You don't compare sort of point by point your galaxy, your mock galaxy to an observed galaxy. You compare summary statistics like galaxy clustering and galaxy lensing. So then you also need ways to make mock observations on your mock galaxy population in order to be able to compare real data. So in Halotools, those are handled in three independent sub-packages. The first is handled by the sim manager. The second is handled by the Empirical Models sub-package. And then the third is the mock observables package. So I thought I would just talk through these three basic sub-packages of Halotools to sort of give a picture for what Halotools is doing. And just to be totally explicit, so for Halotools, the process of running a simulation and then identifying dark matter halos, this happens by the outside world. So this is not what Halotools does. For Halotools, these are inputs. So there's many different packages which are available for both codes for running simulations, codes for identifying halos, and so for Halotools, these are just inputs. So Halotools just takes those as an input and then generates mock galaxies into such a simulation. So starting off with the empirical models. So currently, the simplest bread and butter of Halotools is sort of pre-built models of the galaxy halo connection, which are calibrated against some existing publication. So most common ones being the HOD or abundance matching, stellar to halo mass relation. So you give me a halo mass, I give you a stellar mass of a galaxy which lives in that particular halo. There's also models for the color dependence of galaxies and how that varies as a function of, say, halo mass or as a function of halo age. So each one of these pre-built models you can pick up with a pre-built model factory and sort of immediately load it into memory with one line. And that particular version that you load is always based on a specific publication, which has been fit to some existing data. Okay, and there's about a dozen of these that are sort of pre-built and ready to go, such that in just a few lines, you can very quickly hold a mock galaxy distribution, which looks a whole lot like the particular galaxy sample that paper was fit to. So those pre-built models are all actually just different sort of particular implementations of the model factory design. It's the basic structure of the empirical models package. So the empirical models package is extremely modular. So the way that you build a model is you have just a set of completely independently defined components. You pass them to a model building factory, and the model building factory provides a standardized way to compose those individual features together into a composite model. So all Halotools composite models, no matter what their features are, have the capacity to directly populate dark matter halos with galaxies which have whichever attributes that you decided to include. So each one of these individual features is optional. You can swap features in and out. You can take an existing model and augment it with one new feature, and the syntax for generating a mock galaxy population is identical. And what you get out is an AstroPy table, which stores a collection of mock galaxies which have whichever attributes that you included in your model. So each one of these individual component models also works as a completely standalone feature. So if you don't want to necessarily populate mock galaxies right away, but you just want to study some individual feature, well then you have direct access to its underlying analytical functions, so that you can plot, say, what the concentration mass relation is for your model and sort of study it independently. So this helps both unit testing and also making plots for papers, so that you don't have to generate a mock galaxy population for every individual feature that you want to study. So the reason that I settled on this design was that the usual way of making mock galaxies just requires a huge amount of machinery. And if you're interested in, say, whether or not low mass satellite galaxies are typically, whether they have some memory of their infall history, or whether or not they're perfectly virialized, well then the amount of work that you have to do in order to test how that particular feature, say infall history of satellite galaxies, manifests in, say, the Sloan main galaxy sample, it's a huge amount of work when you only have, say, one particular question that you want to ask. How much does this affect the redshift space distortion, say, for my galaxy sample? So what this design lets you do is just to pick up pre-calibrated components against existing publications, write that one new science feature that you're interested in and no other features, and then just add that one feature into the model and then regenerate a mock galaxy distribution that represents what you would see if the real universe were, as you say, plus all of the things that have been calibrated against an existing galaxy sample. So, okay. That's the basic structure of the empirical models package in a nutshell. So, as I said, Halotools doesn't generate n-body simulations or catalogs of halos, so the sort of bumper sticker there is no halos, no tools. So you need halos in order to be able to use this code. So that being said, I really tried to provide total end-to-end support for starting from nothing and then generating a mock galaxy distribution and computing the clustering in an optimized way. So one of the ways that I do that is through the Sim Manager subpackage. So for example, I really wanted people to be able to just very quickly download contemporary Halo catalog, and within a couple of lines of code to be able to just quickly hold a Halo catalog in their hands in the form of an AstroPy table and to study it. So I provide 20 different Halo catalogs identified with different Halo finders, the different redshifts, different simulations, the different cosmologies that are hosted on my website. The Halotools gives you a sort of a one-liner for being able to download and then to store in cache. So Halotools creates then a persistent memory of what disk location you chose to store that particular Halo catalog. So the Halo catalogs are stored in the form of HDF5 files, which are adorned with lots of metadata, which is used to remind you of how the Halo catalog was processed, to give you information about the simulation that the Halo catalog was generated from, tells you when the Halo catalog was processed in case maybe you chose to overwrite it, and then you can be able to compare the last time that you modified the file with the original processing time. So lots of extensive notes on how the Halo catalog was processed. Each time you load a Halo catalog into memory that's been cached, there's a huge number of sanity checks that are performed automatically for the sort of self-consistency between the actual tabular data that's in the AstroPy table and the metadata associated with the Halo catalog. So all of that I provide, but with Halotools, you're not restricted to just use the Halo catalogs that I created for you. So there's no restrictions on which kind of Halo finder or which kind of simulation that you can use this package with. If you have ASCII data, I provide a tabular sort of lazy ASCII reader, which can handle very, very large files and reduce them into this standardized form that's used by Halotools. But just like the empirical models, the mock generation process is sort of optional. So this cache management system and the use of particular Halo finders is also optional in every respect. So if the only thing you want to use is just this lazy ASCII reader for being able to process hundreds and hundreds of gigabyte files, then I think Halotools would also be useful sort of just for that task alone. So the main thing that then this package does then is it creates a way in order to standardize the basic format of a Halo catalog such that it can integrate with the rest of the package, but those features are completely optional. Okay, so the mock observables package. Right, so as I said, when you have a mock population of galaxies, you don't directly compare galaxy by galaxy your prediction to your observation. You use summary statistics. So for example, you compute galaxy clustering, galaxy-galaxy lensing. You can identify groups, identify clusters in redshift space. All of these functions are available in the Halotools mock observables package. So what we did was we have a customized way of dividing the simulation up into cells and accounting for periodic boundary conditions and computing these very common statistics that people constrain models with. So you have, say, some model for how galaxies are connected to dark matter halos, so how the stellar mass of a galaxy knows about the halo mass that it lives in. And the mock observables package allows you to ask, well, what are the pairwise velocity statistics of central galaxies as identified by, say, my favorite friends of friends group finder? And how does that compare to the exact same statistic that I can measure from, say, the slow main galaxy sample? So there's a very large number of sort of convenience functions for being able to perform these super common calculations in this field of the galaxy halo connection. They're all driven by the same underlying engine. And it's basically the same optimization strategy for each of them, such that it's very easy to add on your particular new variation on this basic structure. For, say, you have some particular marked correlation function that you think is just perfect for identifying satellite quenching gradients in clusters. So there's a very simple pattern that you can match just by adding an individual extra function on top of the ones that are in Halotools that can allow you to design your own statistic, which is optimized for your science target of interest. Okay. So as I said, so each of those individual subpackages works entirely on its own. So I guess I forgot to mention, the mock observables package in no way even knows that you're using the rest of Halotools. So it just takes a set of point data in phase space and returns your summary statistic. Each of these individual subpackages works perfectly fine on its own, but they're also designed to be integrated together, such that any Halotools composite model can take as an input any Halotools formatted catalog and then generate any one of these summary statistics from it. You can swap out individual simulations, just like you can swap out individual modeling features. And you can swap out different summary statistics in the same way. So each of these different summary statistics and each of these different ways of models for generating mock galaxy populations has been optimized with MCMC type applications in mind. So for example, to generate a typical Sloan main galaxy type sample takes about 200 or 300 milliseconds. And to compute the clustering on such a sample takes maybe a second or two. So you can build as many complicated features into your model as you like, and then do really expansive MCMC type analyses using your favorite summary statistic tailored individually for your particular science target. So this is an example analysis that's being done by some graduate students at NYU, which are studying a sort of traditional HOD style model, and they're comparing the clustering statistics, the number density, and in this case, the group multiplicity function. Okay, so that's sort of science targets, just a bit about code. So every Halotools class method and function has a docstring with example usages. Example usages link to step-by-step tutorials for sort of basically all non-trivial functions that are in the code. I make a real effort to have the code not be a black box. So some functions are very involved, like generating Monte Carlo realizations of an NFW profile is a lot of math. And what I do is I create a link to in that particular case, the original Navarro-Franken-White paper that presented this particular form for the profile. I provide a mathematical derivation for the exact equation as is implemented in code, starting from the equation that is in that paper, so that you can look and see what the return value is by that function and see how it follows from first principles. I provide cross-links to the code which tests that function, and also to step-by-step usage tutorials. So basically, thanks to the great convenience of the AstroPy package, or the AstroPy package template, makes this sort of cross-linking with Sphinx extremely convenient and easy for users to see exactly what the math is that leads to the given function that they're choosing to use, and sort of dive into as much documentation as they see fit. Sort of in short, I really try to make the documentation is really a lot more than typical doc strings and code usage. It's basically evolved into a textbook on how to make mock galaxy populations with standard techniques. Okay. So as a sort of testament to how much work I've put into the documentation, there's a large number of ongoing projects that are almost entirely unsupervised by me, and the sort of science targets are very diverse. In most cases, I've given almost no guidance, and the documentation has been entirely self-sufficient for users to pick up the code and very quickly do what they were already doing, and then in a much more flexible fashion. So I think I'll just go ahead and conclude. All right. Okay.
I mean, I guess I would ask the same question. I code. I don't code. I'm usually using other people's. So I'm always looking for like what's happening with the cosmology codes, for example. Maybe you can tell us a little bit more about that, since that would be most of interest to me.
So for which cosmology code?
So you mentioned you have kind of this array here. So there's cosmology with fast PM. So what's going on with that?
Okay, great. So that's a really interesting
Tell me
project
how I could use it, I guess.
that I have had almost no input on at all. But I've spoken with them about what they're doing. So they have their own machinery for generating low resolution simulations based on as a function of cosmology. So they are running an MCMC type chain in which at each step of the chain for a given cosmology, they run a simulation, and then they identify halos in that simulation, and then they just pass those halos to Halotools, and they've chosen an HOD style model, and they're particularly interested in redshift space distortion. So for each step in their chain, they pass their halos to Halotools. Halotools generates galaxies. They use the code to compute the redshift space distortions, and they compare that to observational data of the same statistic. And so this is an example of where they completely ignored the sim manager package, and all they do is just pass in their own halos, which are generated in their own way and are completely different from. It's a very low res simulation, so the halos are completely different from what I've provided.
I have follow-up questions, but I'll ask you later.
Okay.
So we should thank you.
Okay, thanks.
Yeah.